In this video, we're going to move on to logarithms. These functions exist because of what we know about the exponential functions. Recall that when we have an exponential function like y equals a to the x, where a is a positive number that's not equal to 1, the result is always something that's either always increasing or always decreasing, depending on whether a is greater than or less than 1. We always had our graph that was something like this. This is when a is positive, or not positive, when it's greater than 1 specifically. Sorry for the slant on that. And when a is between 0 and 1, it looks like that. It's always something that's always increasing or always decreasing. Specifically, that means it never repeats a y value. It's what we call 1 to 1. And when a function is 1 to 1, it allows us to look at what we call the inverse of the function. Now, you've probably actually heard about inverses from an algebra class. We're not going to spend a lot of time on that. The main thing that we want to note here is that our definition for logarithms is going to be that y equals log base a of x means exactly the same thing as x is equal to a to the y. Basically, we can, if we have this logarithm over here, we pull it over to the other side and it turns into an exponential, the corresponding base of an exponential. We can do this with any base a where a is positive and not 1, but we're going to focus almost entirely on base e. We're going to get what we call the natural logarithm. It's a function y equals ln of x that means exactly the same thing as x is equal to e to the y. So it's a way of taking an exponential e to the x, or e to the y in this case, and turning it backwards, basically. Most of the properties of this natural logarithm will also apply to more general logarithms, but the natural logarithm is nicer when it comes to actual calculus. Now, one thing to also note too is that if you have a scientific calculator, scientific calculators should always have a button for the natural logarithm. So that's this ln button down here. I kind of mentioned this before because that turned out to be connected to the e to the x button as well. It does also have a log button. I'm not going to talk too much about that. This is actually the logarithm base 10, sometimes called the common logarithm. It used to be a very commonly used logarithm back before we had calculators, because calculations could be simplified by using logarithms and the properties of logarithms. It's kind of not as important anymore, but it still exists because the common logarithm found its way into some formulas, especially in like chemistry and stuff like that. So we're almost entirely only going to be looking at the natural logarithm, the ln, that we have on here. But your calculator should have a button for that. Now, what does the graph of the natural logarithm look like? Because this is going to tell us a lot about what the function does. Well, we're going to start with the graph of e to the x. Let's put this in. Let's put it in orange. This is y equals e to the x. Remember, it has certain points on it. It has the point 0, 1. It has a point 1e. There's another point over here. Negative 1, 1 over e. That's e to the negative 1 power. Each of these points will kind of be on the graph of the natural logarithm, except because of this relationship here, anything that was on the outside is now on the inside. Anything that was on the inside is now on the outside. So that essentially just means that we're going to swap our x and y values. So instead of having the point 0, 1, we're now going to have the corresponding point of 1, 0. Instead of having the point 1e, we're now going to have the corresponding point over here of e1. Instead of having negative 1, 1 over e, we're going to have a corresponding point of 1 over e, negative 1. And we're going to end up with a curve that looks like this. Now, if you get more into inverse functions, what you can kind of tell is that if you look at the line y equals x, any function, when you invert it, just reflects over that line. Now, obviously, my picture here is not perfect, but the idea is the same. We get this shape over here. It starts out going down here, approaching the y-axis, and you can kind of tell that comes from the fact that e to the x was approaching the x-axis as we went off to negative infinity. It also will continue to increase as we go because this function over here never loops backwards. It never goes backwards in terms of x's. So this can't ever go backwards in terms of y's. All that kind of stuff. And so we have a lot of properties from this. We have, for the logarithm, we know its domain. Well, the domain of this function is, in fact, the same as the range of e to the x. Because e to the x never gives us a negative y value, we can't get a negative x value for the natural logarithm. So we cannot put in negative numbers, and we can't put in 0 as well. The domain is 0 to infinity. Only positive numbers can be put into the natural logarithm. Nothing else. Our range, on the other hand, because we were able to, our domain for e to the x was everything. We could put in any x value that we wanted. That means that when we switch x and y, we can get out any y value that we want from the natural logarithm. The range of the natural logarithm is literally everything, the entire real line. So we can't put in every number, but we can get every number out. Well, since the domain doesn't include 0, we don't have a y-intercept. And our x-intercept, of course, is 1, 0. We have exactly one of them. And that point is always on a logarithm graph. Not just a natural logarithm. Any logarithm will pass through that point, because any exponential passes the point 0, 1. Property 3, this is continuous. There is no break in our graph, and it's also increasing. Which that will mean, once we actually figure out how to differentiate this, that its derivative has to always be positive. So at least we know something about the derivative already, just from our graph. We also have some limits. If we let x go off to infinity, I kind of mentioned before that this never actually loops back. It never goes downwards again. It's always going to keep increasing. But since it has to cover all the numbers, this has to go off to infinity. On the other side, well, we can't let x go to negative infinity. We can't go past 0, but we can go to 0 from the positive side. If we do that, we're just going to keep decreasing down to negative infinity. So those are all properties that we can get of the natural logarithm just based off what we can get from the graph of it. And we got that graph just based off of e to the x. But there are some other properties of the natural logarithm, more algebraic type properties. If we start with y equals ln of x, remember that was equivalent to saying that x equals e to the y. If we were to just go ahead and plug in the natural logarithm in for y, of course this one just turns into the natural log of x equals natural log of x. That doesn't really tell us too much. But this corresponds directly to x is equal to e to the ln of x. Essentially, putting ln of x into the exponential function e to the x, they kind of cancel each other out and just give you the x that was already in here. Same thing if we put e to the y into here instead of x. So we have y is equal to ln of e to the y, and that corresponds to just over here, e to the y equals e to the y. Essentially, because this formula is always true, then this formula is also true. The fact that this formula is true means that this is true. Essentially here, this is the opposite. So here, a natural log inside of an exponential canceled out and just gave you what you started with. Here, an exponential inside of a logarithm canceled out and just gave you what you started with. Natural logarithms and the natural exponent, those two functions cancel each other out. Kind of the same way roots cancel with powers. So the square root of x squared is supposed to give you just the x, assuming that we're dealing with positive x's, at least. X squared and square root of x are a little bit complicated in that fashion. Think maybe more in terms of the cube root. The cube root of the cube is just whatever you started with. The cube of the cube root is whatever you started with. They cancel each other out just exactly. We also have some properties that come directly from the laws of exponents. So if we have laws of exponents, and I'm just going to write these in terms of e to the x instead of general bases. But remember, we had one property, e to the x times e to the y is the same thing as e to the x plus y. That corresponds to a law of logarithms. Well, notice here that we had a product on the outside of the exponential correspond to a sum inside. When we're dealing with logarithms, remember the insides and the outsides get swapped. So a product on the outside will change to a product on the inside. And a sum on the inside turns into a sum on the outside. Basically, we have the natural logarithm of a product, natural logarithm x times y, is equal to the sum of the natural logarithm x and the natural logarithm of y. Kind of the same thing when we have division. E to the x divided by e to the y is equal to e to the x minus y. The division on the outside is going to turn into division on the inside. And the subtraction on the inside is going to turn into subtraction on the outside. Finally, we're going to look at the property e to the x then to the y. Remember, when we had a stacked power like this, it's the same thing as e to the x times y. One might be a little harder to see exactly how this corresponds. But what this actually ends up giving us is that a power on the inside, so the natural logarithm of x to the y power, is the same thing as if I take the natural logarithm of the base x and I multiply that result by y. That does actually directly come from this property over here. It's just maybe not quite as clear why that's the case. These aren't really that too bad to prove, but let's just do the first one. So we want to prove that the natural logarithm x plus y, natural logarithm of x times y is equal to the natural logarithm of x plus the natural logarithm of y. And I'm going to do this by actually calling, I'm going to call this one here, let's call this, let's call it s. I'll call this one t. The natural logarithm of x plus the natural logarithm of y. If I'm calling those s and t, this is just s plus t. Well, remember, the natural logarithm and the exponential function cancel each other out. I can actually go the other way as well. So I can start with something that's on the outside and turn that into the natural logarithm of e to that power. So s plus t is the same thing as the natural logarithm of e to the s plus t. Might seem a little weird to do it that way. Seems like we're just making things more complicated. But the point here is now I have e to a sum, and I can use my laws of exponents. That was my entire point, was to try to get to a law of exponents. E to the s plus t is the same thing as e to the s times e to the t. But now I know what s and t are. We have the natural logarithm of e to the ln of x, because that's what s was, and e to the ln of y, because that's what t was. And now I can use my other property, that e to a natural logarithm cancel each other out. So e to the ln of x is just x. E to the ln of y is just y. So ln of x plus ln of y is the same thing as ln of x times y. And all of this came from the fact that I have that law of exponents, and I have my way of switching between natural logarithms and the regular natural logarithms and the exponential function. Let's go ahead and do a couple of examples where we use these laws of exponents, laws of exponents and laws of logarithms in order to maybe simplify a few expressions. Look at problem 29. We have the natural logarithm of xy over z. I probably should note here, I've been putting parentheses on here pretty consistently. The book actually writes it as just natural logarithm of xy over z. For whatever reason, people will sometimes drop the parentheses on these. I kind of like having the parentheses in there just to make it clear what's inside of the logarithm, but some people in the book don't. It can be a little bit confusing, I admit, but that is kind of standard for some reason. But the point here is I want to turn this natural logarithm into some simpler logarithms. Now you have this complicated expression inside of the natural logarithm. I'd like it to be a little bit simpler. I'm going to go ahead and use my laws of exponents. First things first, I have a quotient. Inside here I have a quotient. The logarithm of a quotient is a difference of logarithms. And it's going to take my numerator as my first logarithm, and my denominator as my second one. But then we have a natural logarithm of a product. The natural logarithm of x times y is the same thing as the sum of two logarithms. We have natural logarithm of x plus the natural logarithm of y. We saw the minus the natural logarithm of z at the back. So instead of having this complicated expression, now we can actually just write it as the sum or difference of three different logarithms. If we look at problem 31, we have the natural logarithm of the cube root of 2x plus 7. Again, this is how the book wrote it. If we want to be kind of specific about it, we can go ahead and treat this as having parentheses around it. This time it's not quite as unclear because the cube root already kind of tells us what's inside there. But you might be wondering, how can we simplify this one? Well, remember, the cube root is a power. This is the natural logarithm of 2x plus 7 to the 1/3 power. And we have a rule that says if we have the natural logarithm of a power, that power can be pulled out in front. Even that if that power is not an integer. If that power is a 1/3, we can still pull it out. This is the same thing as 1/3 times the natural logarithm of what was already inside there, the 2x plus 7. Now note we can't split this up any further. The 2x plus 7 is kind of a stopping point. We do not have a property that deals with a sum inside of the logarithm. Our only property of logarithms that we can work with are ones that have a product, a quotient, or a power inside of the logarithm. If there's a sum outside, we can deal with it. If there's a sum inside, we do not have a rule for that. So once we get to some sum of stuff, it usually denotes where we have to stop. Now, sometimes we can get around that if we can factor stuff. We'll see that in this next problem. Problem 36. Here we have the natural logarithm of 2x over the square root of x squared minus 1. Again, we can go ahead and put parentheses around it if there's any confusion. We want to split this up into the simplest logarithms we can. First thing, we have a quotient. So we take a natural logarithm of the top minus a natural logarithm of the bottom. Next thing, we have a natural logarithm of a product. We can turn this into the natural logarithm of 2 plus the natural logarithm of x. Here, I can do the same thing that we did in 31, where here we have the cube root was a power of 1/3. Here, the square root is a power of 1/2. I'm going to skip the step where I write it as a power of 1/2 and just turn this directly into minus 1/2 the logarithm of x squared minus 1. That's one really nice thing is that the logarithms get rid of any of these square roots or cube roots or any of those. And like I said before, this might indicate that we are at a stopping point. We have a difference of things inside the logarithm. But note that we can factor x squared minus 1. We can go ahead and factor that as x minus 1 times x plus 1. And once we factor it like that, we could go ahead and split this up. Essentially, this is the logarithm of x minus 1 plus the logarithm of x plus 1. Do note that we do have to distribute the negative 1/2 to both of those logarithms, though. So we have minus 1/2 the logarithm of x minus 1 minus 1/2 of the logarithm of x plus 1. So this would be the simplest way to write this. I do want to caution you, however, that you might not want to do this last step if you don't know what your x values are, because note we could put in negative 5 into this x here. The square would turn that into a positive 25 minus 1, and you'd be taking the logarithm of 24. That's perfectly fine. But if you instead put negative 5 into here, negative 5 minus 1 is a negative 6. The logarithm is not defined for negative 6, nor would it be for the negative 4 that we'd have over here. So, in a way, this doesn't work if for some x values. That has to do with the fact that the square was getting rid of any of our negatives. So we have to be a little bit careful for those kind of reasons. But as long as we're dealing with x's that all these are defined for, these are going to be equal to each other. We can also use these properties of logarithms and the connection between exponentials and logarithms to solve equations that involve either an exponential or a logarithm. Let's look at problem 51. Here we have an equation, 300 times e to the negative 0.2t is equal to 700. Now, you might wonder where might such an equation come from? Well, maybe it came from something like our compound interest formula. Maybe we knew what the rate was, and we know the principal and the amount. And well, we know the principal is 300. Our rate was negative. Well, probably doesn't really apply here because that negative rate would be kind of weird. But maybe you get the idea. If we had a positive number here, we might have a principal and we know the rate, and we want to know how much time it would take to get to a final amount, and we might have to solve for that reason. But the fact that we get these kind of functions in our examples means that it's actually not too uncommon to have to solve this kind of an equation. So how do we solve it? Well, the first thing I'm going to do is I'm going to divide out by the 300, which cancels the 100 part of that, but we're left with a 7/3. But remember, now we have e to some power equals a number. This is equivalent to saying that the power is equal to the natural logarithm of the number. Remember, we can essentially get to pull the e to the other side and turn it into a logarithm. It's the same thing as if we had a square over here and we take the square root over to the other side. Then we can just go ahead and divide by negative 0.02, or sorry, negative 0.2. And that looks like a very complicated expression, so we just go ahead and use a calculator. And we get an answer of negative 4.236, and so on. That is the t value that makes this work out. Let's look at problem 59 now. This one goes the other way. This is a formula that involves a logarithm. Now, these are a little less common than the ones that we had up here, but we still want to be able to deal with these kind of things. Now, once again, sort of like what we did up here, is the first step we want to solve for our logarithm. Here, the first step here, we wanted to solve for our exponential, so we can use our property. Here, we're going to solve for the logarithm. So we'll subtract 3 from both sides. Divide by 4. This time they gave us numbers that work out pretty nicely. Now we're left with the natural logarithm of something equals something. We can turn that into an exponential equation. Basically, the stuff that was inside is now outside, and the stuff that was outside is now inside an exponential. The x here is e cubed, which is about 20.0855. So notice both in pretty much all these cases, the thing you want to do is get a single logarithm or a single exponential is equal to a number, so that we can use our defining property of the logarithm in order to swap from a logarithm to an exponential or vice versa. So look at problem 65. So this is going to look pretty similar to the one we just had, though there'll be a little bit of a difference. We have 500 times 1.07 to the t power is equal to 1,000. We can go ahead and solve for our exponential and get that 1.07 to the t power is equal to 2. Well, we don't have an e to the x in here. Instead, we have a different exponential. We have a different base. We have 1.07 as our base. If we wanted to use logarithms, we could actually turn this into t equals the logarithm with a base 1.07 of 2. But remember, our calculator has a button for the natural logarithm, and maybe for the common logarithm, the ln base 10. We don't have an ln base 1.07 on our calculator. So we probably don't want to go that direction. We want to get something that we can compute. So what do we do instead? Well, we can actually use the natural logarithm itself instead of the logarithm base 1.07. What we do is we take the natural logarithm of both sides, and now we can use our properties of logarithms. Remember, the natural logarithm of some power means that we can take the power out in front. This is the same thing as t times the natural logarithm of 1.07. And this really isn't a logarithm problem anymore. It's t times some number equals some number. This is just a linear equation. We can just go ahead and divide out by this logarithm. T is equal to ln of 2 over ln of 1.07. These are numbers we can plug into a calculator. Turns out when we do that, we get 10.2447 and so on. So using the natural logarithm on these exponential equations allows us to solve it for any exponential that we want. We can even turn this process into a theorem, into a property. If we start with y equals a to the x, we take the natural logarithm of both sides, and then we use our property of logarithms to turn this into x times the natural logarithm of a. We can solve and say that x is the natural logarithm of y over the natural logarithm of a. But like I said, by definition, let's say x equals the log base a of y means that y equals a to the x. That's what this logarithm even means. So if x is the same x in both of these, because it is the same formula, y equals a to the x, then these two x's have to be equal to each other. Basically, the logarithm base a of y is the same thing as the natural logarithm of y divided by the natural logarithm of a. So we can compute any logarithm we want to any base, as long as that base is positive and not 1, by using this formula. This is called the change of base formula. Because we changed from this base a to a base e. Technically, we could also use this for a different base over here as well, but that's not too important right now. The main point here is that we can go ahead and find these logarithms by using just the natural logarithm. And the fact that this exists is why calculators don't bother with a more generic logarithm button. We only need that natural logarithm. You could also do this with the common logarithm as well. You could say this is equal to the common logarithm of y over the common logarithm of a. You don't really have to do that, but it is possible if you wanted to do that. All right. So we're not really done talking about logarithms. We're going to save the derivative of the logarithm till next time. We're going to have a whole section on that, and we'll actually even use that to find formulas for the logarithm and the exponentials of different bases. We know the derivative of e to the x. what's the derivative of 2 to the x? We'll be able to find that next section. So I'll meet you there.